Hi friends, welcome to follow up. Let's have a look at problem 399. Evaluate division. This is today's daily challenge problem. So in this video, I'm going to present a solution based on the use of graph. So here the main motivation is that we want to demonstrate how to decompose this problem into ingredients, and then we solve each of the ingredients separately. Together they form a solution to the problem. Actually, you will find that if one can separate the task here into small subtasks, then the problem becomes organized or easier, right? So here in this problem, we are given an array of variable pairs called equations, and an array of real numbers called values. So the equations I is AI BI, and the value I represents the quotient of AI over BI, right? So each AI and BI is a string that represents a single variable. So we are also given some queries, where queries J is CJ represents the J's query, where we must find the answer CJ over DJ. So we are required to return the answers to the queries. So if a single answer cannot be determined, so we are going to return -1. So here is a note. So the input is always valid. We may assume that evaluating the queries will not result in division by 0, and that there's no contradiction, right? So here are some examples. For example, in example 1, so if we are given A over B is 2 and B over C is 3, then we can get A over C is 6, right? So that's basically a chain of computations. So similarly, you can interpret example 2 and example 3. So in this problem, actually, there's another case. For example, if you have some graph and you have some queries, for example, you have x. So this x does not appear in the equations as a variable. So in that case, even we have x equals x, we need to return -1 due to the problem requirement. So that's one point we need to notice. So let's also look at the constraints. So the constraints are actually the additional assumptions for the problem. First, there are at most 20 equations, and the equations has length 2, and this is the variable length, right? It's bounded above by 5, and the values are strictly greater than 0, and the query length is bounded by 20 above, and CJ and DJ length is the same as the variable name. So AI, BI, CI, D, and CJ, DJ consist of lowercase English letters and digits. So with that said, basically we can do the coding. So we're going to explain the logic when we do the coding. So here actually we are going to split the solution into 3 parts. So the one part is to build the graph. So we want to establish the connections or relations between variables, right? So especially like chained, right? So for example, we can arrive from A to B, there's a direct edge, and then from B to C is another edge. Then we can arrive from A to B, then to C. So in other words, or in graph theory terminology, there is a path from vertex A to vertex C, and then the corresponding values actually is multiplied, right? So if you are familiar with some deep learning libraries like PyTorch or Keras and TensorFlow, and then you have some, you might have met the concept computational graph. So here actually it's sort of a computation graph. So this is the one thing. Another thing is that we want to write a breadth first search for getting the shortest path, between 2 vertices, right? In the process, we also want to find the the result of the beginning or the source over the destination of the path, right? So lastly, we just need to use list comprehension to return the required format. So now let's look at the coding part. So the first part, I'm going to build a graph. So we can regard this here as a computational graph. So for this, I'm going to initialize a capital G as a variable. So I'm going to use collections and default dict. So here I'm going to use a dictionary. The reason is that I want to, for each neighbor, I want to save the quotient between the node and its neighbor. In other words, the node will equal to the quotient times the node. So this is the equation relation. So basically, for this, I just need to iterate, right? So for vertices u, v, and also the quotient in zip equations and values. So what I'm going to do is so gu. So this is a dictionary, right? So if we have v, so we're going to set gu of v equals q, which means that u equals q times v. That's the equation. So on the other hand, we needed to do this because if u have and v have such a relation, so we know vu will be 1 over q. In other words, so v equals u 1 over q times u, right? Uh, 1 over q times u. So in other words, this is the reverse equation for this. So here this two part is interpreted mathematically. Here just interpret vq and u1 over q as key value pairs. So this way we finished building the computational graph. So now let's look at the second one. So that is find path between a source and a destination. So for this, I'm going to define a utility function that is find path. So we have a source, we have a destination, right? And then here, let me first do a check. If source not in graph or destination not in graph. If this is the case, so here let me add some parentheses. It's not necessary, but I want to add it to make the logic clear. So if either of the two ends not in the graph, then we're going to return -1. So this is the problem requirement. So here, actually, this one I tested. So if you have a query such as, for example, you have a query like x and x, for example, in example 1, right? So we need to return, the corresponding return is -1 rather than 1, because x and x is the same, right? And intuitively, we might consider return 1, but the requirement is -1. So that's why we add this check. So in other words, if the source or the destination is not in the graph or not come into play, we're going to return -1. So next is the basic depth first search function. So here I'm going to use this visit set to help us avoid repetition during the traversal. And here, because we want to find the shortest path between the source and destination, I'm going to use depth breadth first based solution. So here collections deck. So I'm going to use this one. This way I can use pop left. So here we have source, right? So the original result will be 1, right? The starting point, and then the while loop. So here this is a node and a value. So this value is nothing but the value equals the source over the node value mathematically, or using the relation determined by this graph. So for example, the current node is source itself, the value is 1. So then, well, the queue is not empty, then this standard breadth first based traversal if you do not consider this 1 as the value. If node and the value, so let's see, if queue is not empty, so we pop this one, so we're going to get queue pop left, right? And then what we want to do is first a check, right? If node equals a destination, right? We just need to return the value. Otherwise, we check if node not in visited. So if this is the case, so we're going to add this current node to the set, and then we check its neighbor. So neighbors, for neighbor in graph node, right? And then what we are going to do is check if neighbor not in visited, right? Then we are going to do append. So here we want to notice what we should append. So we should append neighbor and the value of source over a neighbor, right? The source over neighbor is nothing but source over node, right? Times node over neighbor, right? We know that for the source over node is nothing but this value, right? And then for the node over neighbor is nothing but G node and neighbor. So that's exactly what we do when we build the graph. So this will be the utility function. Otherwise, we're going to return -1, right? So we either return the quotient of source over destination, or if we cannot find, we're going to return -1. So this is the utility function. Now the third step will be prepare the return. So this is very straightforward now. We just do return, and then what we're going to do, so we call this function find path, and then we have a source and the destination. So basically for this query in queries. So this query is a list2 list, right? So we can pass it as a tuple or just use query, right? So this star notation basically says, oh, I'll pass this element in the query as a tuple. So basically it's a UV, right? UV is the query representation. So this code actually forms a solution format. So if you directly think a solution without splitting the solution into different parts, it might be slightly harder. However, once we split the problem into these 3 parts, so each part is actually a very routine task, right? Build a graph and write first based traversal. But we add the problem logic inside. And then the last one is just the return format. So before we make any further comments, let's first do a check. Yeah, it passes the first example. Especially we need to notice that for this x and x, we need to return -1 rather than 1. But if we want to return 1 in some cases, we can also achieve that. So basically, if source equals destination first, basically we return 1. If we want not -1 but 1, if we want to do this, right? But this is just a set comment. Let me comment out this. So now let's do a generic case check. Yeah, it passes all the generic cases. So here is a wrong submission. So here the wrong submission is due to here, right? Due to this case. So I guess AA. So yeah. Oh, this is not the one this is 2 years ago. Let's see. Let me look at the submissions. So I guess I had a wrong submission, which I forgot to add this check, right? But you need to pay attention to that part. So I guess with that explained, that's about it for this problem. So overall, so this is a um, so this is a graph problem. So here, what we do actually is split them into three parts. One is computational graph, and the other is breadth first search for shortest path, and then a list comprehension. So with that said, I guess that's it for this video. Thank you.